thank you very much. This is Cheung. I'm from Singapore University of Technology and Design. So I did a lot of work on video compression, video coding. For the interest of time, I also try to compress this talk and see how I can conclude. And the topic is layer coding for mobile cloud gaming, and this is a joint work with my coworker, Seong-PIng. So this talk is about mobile cloud gaming. Cloud gaming attracted a lot of attention recently, and in cloud gaming, the client will send the game control and button press to the cloud server, and in response, the cloud server will execute the game logic, render the game images, and transfer the game images back to the client for display. In particular, the game logic and the game data are resided on the cloud server, and also computational intensive rendering are executed on the cloud server, and the game images are transmitted back to the client for display. And mobile cloud gaming attracted a lot of attention and may offer some opportunities and advantages. In particular, it has potential to transform the mobile devices into powerful game engines so that we can have photorealistic rendering on the free mobile clients. It can also enable gaming on the go, and we can have high-quality game content on the mobile devices anywhere and anytime. However, there are some technical challenges for mobile cloud gaming. In particular, bandwidth consumption and latency are the main technical challenges for cloud gaming. For cloud gaming, it is very expensive to transmit these high-quality game images from the cloud to the client. And the contribution of this work is we try to propose a novel framework so that we can reduce the bandwidth for transmitting these high-quality game images from the cloud to the client. And we refer this approach as layer coding, which I'm going to discuss. And the idea of layer coding is to leverage the client computation to reduce the transmission bandwidth for sending these high-quality game images. Increasingly, mobile devices will have some rendering capability, and we attempt to leverage this rendering capability to reduce the transmission bandwidth for sending these high-quality game images. In particular, in our layer coding, the client will render a low-quality game image or the base layer on the mobile device, and the quality of this base layer is limited by the computational capability of the mobile device. And on the cloud server, instead of sending the high-quality game image directly from the cloud to the client, the cloud will generate some enhancement layer information. And in addition, the cloud will send this enhancement layer information to the client. And the client can utilize this enhancement layer information to improve the quality of the base layer image to get high-quality game content. And this is the basic idea of layer coding. And I will discuss how to generate this enhancement layer information in a moment. But if this enhancement layer information requires less bandwidth than the high-quality game image, then we can achieve bandwidth reduction, and at the same time, we can have high-quality game content on the client. And this is the system diagram for layer coding. And in response to the game control, the cloud server will render both the high-quality game image and the base layer image of the same game scenes. And on the mobile client, an identical base layer image will be rendered using the base layer rendering pipeline. And we propose to generate this enhancement layer information as the difference between the high-quality game image and the base layer image. To generate this enhancement layer image, we would subtract the base layer image from the high-quality game image in the pixel domain. And we further compress this enhancement layer image using H.264 intra-frame coding. And the encoder enhancement layer information constitutes the enhancement layer information that is sent from the server to the client. So I have discussed how to generate this enhancement layer information. However, there's still one key design question remains. how to design this base layer rendering pipeline so that the information of the enhancement layer can be minimized and so that we can use as little bandwidth as possible. And as you can guess, there could be many different approaches to perform this base layer rendering. And some base layer rendering configuration will be able to result in less information in the enhancement layer and also achieve more bandwidth reduction. And this is the problem we are going to look into, how to design this base layer rendering for layer coding. And in particular, as based on our discussion, essentially what we are doing is we try to partition the information of the high-quality game image into enhancement layer information and base layer information. So we partition this information into enhancement layer information and base layer information. And the enhancement layer information would consume bandwidth, sending the enhancement layer information would consume the bandwidth from the account to the client. And to generate this base layer information would require client computation. And the more base layer information we can generate, the less information the enhancement layer would contain, and therefore the less bandwidth we would require. So therefore, our goal is to try to generate as much base layer information as possible by the mobile client. However, this is constrained by the capability of the mobile client because generally this base layer information would require client computation. And therefore, to formalize our design problem, we try to seek the base layer rendering configuration so that we can maximize the base layer information subject to the computation constraint of the mobile device. And mathematically, this is how what we try to do. We seek the base layer rendering configuration file that can maximize the base layer information based subject to the computation capability. So we have discussed the formulation for the base layer rendering design, and basically we try to achieve this goal to maximize the base layer information. However, to determine this rendering configuration that can maximize this equation is still quite complicated. This figure shows the modern 3D rendering pipeline, and it is very complicated, involve different stages, including vertex processing, rasterization, fragment processing, and output merging. And it is very complicated, so it is difficult to determine a global optimum configuration to achieve this goal. And in this work, we focus on fragment processing. In particular, we look at phone lighting. And phone lighting models the interaction between the light sources and the objects in the 3D scenes. And phone lighting accounts for considerable amount of overall computation because we have to perform lighting computation for each fragment. And we also have major impact on the quality of the file image. And in this work, we propose how to scale the phone lighting so that it can be executed on a range of power-limited mobile device, and while trying to achieve this goal to maximize the base layer information. And to scale the phone lighting, we propose to perform computation using subset of reflection components and light source. For phone lighting models the surface reflection as the combination of three reflection components: ambient, diffuse, and specular. And different reflection components would require different amounts of computation. For instance, specular reflection components would require the most amount of computation because it involves this exponent operation. And also, more important, different reflection components also render different amount of information into the image. For instance, the diffuse reflection component would render smooth and spread lighting into the image, while specular reflection would render isolated and sparse lighting into the image. And therefore, in our work, we propose technique to estimate the information contribution. So we propose technique to estimate the information contribution by different reflection components. And In the base layer rendering, we would choose those reflection components that have significant information contribution. And in particular, to do this, we estimate the information contribution per computation for each for different reflection components. And in the base layer rendering, we will only choose those that have significant information contribution. And for those that are not included in the base layer rendering, the information is communicated by the enhancement layer. And in addition to reflection component, we also try to scale phone lighting in another dimension using light source. And for a typical game video scene, we might have multiple light sources. And different light sources will also introduce different amount of information into the image. In particular, some light sources will illuminate more pixels than the other because of their stronger intensity or because they have matching angle of illumination. So we also try to estimate the information contribution by each light sources, and we will, in the base layer rendering, we will include only those light sources that have significant information contribution. So to summarize, to scale the phone lighting, we try to perform computation on subset of reflection components and light source, and they are chosen based on their information contribution into the image. And this figure shows the scalability of phone lighting based on our algorithm. The horizontal axis represents the phone lighting computation capacity, and the vertical axis represents the base layer information. And different circles represent different phone lighting configuration with different number of reflection components and light sources chosen based on their information contributions. And for instance, for this one, we include all the reflection components and light sources, and therefore it requires the maximum capacity, and it can also generate the maximum amount of base layer information. And what is significant here is that we can actually, by choosing the reflection component and light source carefully, we can generate more than, the base layer can have more than half the information by performing only 10% of the phone lighting computation, as you can see this configuration. So therefore, by choosing the reflection component and light source carefully, we can actually scale the base layer information very efficiently with respect to the computation. So then I would like to discuss some experiment results, and to test our idea, we generate some game animation, and they are created by Blender, which is an open source computer graphics software that can be used for video games. And we compare two approaches. The first one is direct coding, which is the state of the art that is used by cloud gaming. They use H.264 for interframe coding, and this is compared with our proposed layer coding, which we use a base layer rendering pipeline that includes only a subset of reflection component and light source. And showing here are two game animation sequences. The top one is compressed by direct coding. This is what people are doing. And the bottom one are coded by our proposed layer coding. As you can see, they have almost similar subject quality. However, in our case, we use about 30% of bandwidth compared with direct coding. And this figure shows the weight distortion comparison between direct coding and layer coding. And we have three different game animation with different model capacity and different amount of object motion. And the horizontal axis represents the bit weight, and the vertical axis represents the quality of the game image. And as you can see, and the green one is the layer coding, and the blue one is direct coding. And as you can observe, our layer coding can achieve substantial bandwidth reduction with respect to what people are currently doing. To conclude, we have proposed a layer coding to reduce the transmission bandwidth of mobile cloud gaming in particular, our idea is to leverage the current computation to reduce the transmission bandwidth for sending this high-quality game image. And we have formalized the base layer rendering pipeline design, and we have also proposed a scalable phone mapping so that it can be executed on a range of power-limited mobile devices, and by choosing different repression components and light source carefully. And experiments suggest that layer coding compares favorably with direct video coding of the game image. And this is the end of my talk. Thank you very much.
So I think we've got many video encoding specialists here in the audience. So I think we have time for one question for Ngai-Man.
So recently, without your scheme, have you measured the power consumption on mobile devices? Are you going to reduce the power consumption on the mobile device, or you are going to increase the power consumption?
Right. So in fact, we will increase the power of the mobile card. So we leverage the power. We try to leverage the power of the mobile cards to reduce the bandwidth. We see the opportunity that some of the mobile cards now have some rendering capability, and therefore we use this computation of the mobile card and to do something so that we can reduce the bandwidth. So we trade the computation for bandwidth.
No, but you also reduce the amount of traffic you are going to send, right? So
right.
communication power consumption is going to be reduced.
That's that would be true. That would be true. I mean, that's a very good point. And because we actually reduce the bandwidth, so we might actually end up with spending less energy in the transmission and doing the computation. We didn't measure that, but that's very good point.
So I really love your work. It's really awesome. But so have you thought about, so previously with cloud gaming, your client is just a video player which just captures commands and streams video and plays it. But now here, with your approach, you have to know about game logic. You need an exact replica of the game on the client side as well. So you're not a video player anymore. You need a sophisticated game engine. How do you think that will work on mobile devices?
Right. That's a good one, but that might not be true. I mean, we thought that it might be actually possible for the game logic to execute on the card, but we send the game command to the card. So kind of the rendering command to the card. So card will basically does not execute the game logic, but it will receive this rendering command how to do the rendering.
But then you need to include the rendering command into the...
Right. So I think the rendering command will be much simpler than the game images, but that's true.
But besides the command, you also need to send the data in the video card.
Right. You also require some of the models in that, but usually in a game, you don't update that very often. So for game image, you update this at 30 frames per second. But for the model, you might actually send this as when you start your game session, and then you send this update maybe after a while also. So the amount of traffic is actually quite different from the game images. But that's also good point. We require to communicate the model information to mobile cards.
Okay, I think let's thank the speakers again. And